Hello everyone, Mr. Clark here. Title of today's lesson, Combining and Resolving Vectors. This is our second lesson of the Mechanics unit at Excel Unit 2. Learning intentions for today, understand how to combine and resolve vectors. And you can see the success criteria there. We'll refer back to that at the end of the lesson. Starter activity, this can be on just a rough piece of paper. Draw a free body force diagram for a block on a ramp, as shown in the diagram. So a free body force diagram is a diagram which shows all of the forces acting on one object. So try and consider all of the forces acting and draw those onto your diagram. Pause the video to do that. So your diagram should look something like this. We know that weight acts directly downwards from the centre of mass of the object. We've got a reaction force R, which is due to the surface pushing back up on the block, and we have got a frictional force F, which is pulling the block back up the slope. So we've got three forces labelled F, R and W in the direction shown. So we'll come back to our force diagram in a moment. Let's just have a think about combining displacement vectors. Let's say we go on a walk, we draw displacement vectors for each part of that walk. How could we combine these to see where we end up? We can add the vectors tip to tail. We join the start and end points on our diagram to find the resultant vector. So you can see in the diagram here, the vectors have now been added tip to tail, and we then join the start and end points to find the resultant vector. So does the order matter? No, the order in which we add the vectors doesn't matter. So the second diagram here shows the vectors added together tip to tail in a different order, and we should get to the same point. So we've got the same starting points, same end points, and so our resultant displacement vector is going to be the same. So the red arrow should be the same size and direction as in the first diagram. So back to our block on the ramp. Consider all the forces acting on the block. If we place these force vectors tip to tail, what shape will it make? So we know the block was or is in equilibrium, it's not moving. So the vectors should join up to form a closed polygon. The body is in equilibrium. What is the resultant force? So if the vectors join up to form a closed polygon, the resultant force is 0. And you can see from the triangle here, or the vector diagram, we've added the vectors tip to tail, and we can see it forms a closed polygon. This is sometimes called a vector polygon or a vector triangle. Combining perpendicular vectors. To find the resultant of two vectors acting at 90 degrees to each other, we draw the vectors as adjacent sides of a rectangle. The resultant is the diagonal of the rectangle, as shown here, with the red arrow labelled resultant R. The magnitude, size of the resultant vector R, can be found using Pythagoras' theorem. So R squared equals x squared plus y squared, referring to the diagram. How can we find the direction of the resultant? So to find the direction of the resultant, given by angle theta in the diagram, we can use tan theta equals opposite over adjacent, which equals y over x. So theta equals inverse tan of y divided by x. We can also find the resultant vector from scale drawing and measurement of the angle with a protractor. An example of combining vectors, perpendicular vectors, is given here. We're looking at velocity vectors. This can apply to any type of vector. A man tries to row directly across a river. He rows at a velocity of 3 meters per second. The river has a current of velocity 4 meters per second parallel to the banks. Calculate the resultant velocity of the boat. So the first thing to do is to construct the vector diagram as shown here, and to draw in the resultant vector, and that gives us a clear picture of what we are trying to find. So we can find the resultant using Pythagoras. Size of resultant, 3 squared plus 4 squared square root equals the square root of 25, which equals 5.0 meters per second. Direction of resultant, tan theta equals opposite over adjacent, which equals 3 divided by 4. The theta equals inverse tan, 3 divided by 4, which equals 37 degrees. So the resultant velocity is 5 meters per second at 37 degrees to the bank. Practice using your calculator and the tan function and inverse tan function to make sure that you can calculate this value correctly, and just to make sure that your calculator isn't stuck in a funny mode or something. This is a worked example where I'm going to get you to have a think about it first and have a go, and then we'll go through it together. 2 tugboats are pulling a ship into harbour. I don't know if you've ever seen these little boats that steer the big ships around, pull them around. One tug pulls in a southeast direction, the other pulls in a southwest direction. Each tug pulls with a force of 8.0 times 10 to the 4 newtons. So that's 80,000 newtons. What is the resultant force on the ship? So we've got the vector diagram shown here. We construct that. That's the first thing we would do. So have a go at sketching the diagram. We know the two forces at 90 degrees to each other, if one is southeast and one is southwest. We're going to use Pythagoras to calculate the resultant. So go ahead and use Pythagoras. So Pythagoras gives us the magnitude of the resultant. So it's 8 times 10 to the 4 squared plus 8 times 10 to the 4 squared, square root, is going to give us 1.1 times 10 to the 5 newtons, which is 2 sig fig. Since both tugs pull with the same force, the vectors from adjacent sides form adjacent sides of a square. The resultant is the diagonal of the square, so it acts at 45 degrees to the vector. The resultant force must therefore act due south. We could do a tan theta equals opposite over adjacent, and we'd find that the angle is 45. So we've just done combining vectors. We are now on to resolving vectors, which is where you have a single vector, a result vector, that you want to break down into 2 components which are at right angles to each other. The components of a vector tell you the effect of the vector in that direction. This can be particularly useful when we are trying to combine vectors. We'll see later that we use this in moments and in projectile motion. So it's an essential piece of knowledge that we need now. Taking the angle theta as labelled there, from your GCSE maths you will have studied trigonometry, and you may have met the term SOHCAHTOA. That is just a little aid memoir which allows us to remember that cos theta equals adjacent divided by hypotenuse, and sine theta equals opposite divided by hypotenuse. Tan theta equals opposite divided by adjacent. So what we're going to do is come up with an expression involving V1 and V first, and then an expression involving V2 and V. So cos theta, adjacent over hypotenuse, is going to equal V1, divided by v. So that then gives us v1 equals v cos theta. Sine theta is going to be equal to opposite over hypotenuse. So that's v2 over v. So therefore, v2 equals v sine theta. In the red box there, I've written them as vx and vy, because that's quite often how you get the problem with one in the x direction, one in the y direction, but it's not always the case. So an example of resolving vectors: a tennis player hits a ball at 10 meters per second at an angle of 30 degrees to the ground. What are the initial horizontal and vertical components of the velocity of the ball? First thing to do is to sketch the vector diagram. Have a go at doing that. And then we can use our vector components. So VH equals V cos theta, which equals 10 cos 30, which equals 8.7 meters per second. And V vertical equals V sine theta, which equals 10 sine 30, which equals 5.0 meters per second. So you can see we've got a horizontal and vertical component of that vector. Taking another example of resolving vectors, this is a water skier. A water skier is pulled up a ramp by the tension in the tow rope. This is a force of 300 newtons acting horizontally. The ramp is angled at 20 degrees to the horizontal. What are the components of the force from the rope acting A, parallel to, and B, perpendicular to the slope? So we draw the vector diagram. You've got the diagram actually given there, which I think is helpful in this case, but sketch anyway and see if you can answer the question. So we take the components, we resolve vectors, and we find the components. The parallel component, F parallel, is 300 cosine 20, and the perpendicular component is 300 sine 20. So that gives us the values shown here. Parallel component 282 newtons, perpendicular component 103 newtons. And we could test that that's correct by using Pythagoras and working back the other way. So taking things a step further and using all of our knowledge so far, we're going to look at combining non-perpendicular vectors by calculation. Take this example. Three forces act on a single point, as shown in the diagram. Find the magnitude and direction of their resultant force. Step 1 is to resolve the 3 Newton force into its horizontal and vertical components. Have a go doing that. Pause the video. So that will give us, for the 3 Newton component, in the horizontal direction, 3.0 cos 30, and, or we can say sine 60. And in the vertical component is 3.0 cos 60, using the angle 60 that's shown there. So we get 2.6 newtons horizontal and 1.5 newton vertical. What we can then do is replace the 3 Newton force with its components in the diagram shown in black, and then we can combine those with the other forces. We now have a situation where we're combining linear forces. So the total horizontal force equals 6 minus 2.6, which is 3.4 newtons to the left. And the total vertical force is 2.0 plus 1.5, which equals 3.5 newtons downwards. So now we have a single horizontal component and a single vertical component. We can combine those together to find a single resultant force, shown in the diagram there. So we use Pythagoras like we were doing before. So to find the magnitude, we use Pythagoras. So it's 3.4 squared plus 3.5 squared, all square rooted, which is 4.9 newtons, 2 sig fig. And then we use tan theta equals opposite over adjacent to find the angle. So 3.5 over 3.4. Theta equals inverse tan, 3.5 over 3.4, which is equal to 46 degrees. Theta is the angle shown in the diagram. So the resultant force is 4.9 newtons acting at 46 degrees below the original 6 Newton force. So there we go, we've combined together non-perpendicular vectors by calculation. So well done if you have completed everything successfully. So just a quick check now, the success criteria. We were looking for you to be able to combine vectors to find the resultant vector. We looked at perpendicular components, and we also looked at using vector diagrams. Know that a closed vector polygon equals a zero resultant. Use a scale drawing to determine resultant forces. Know how to do that. And calculate resultant force using Pythagoras theorem, and resolve vectors using trig to find the components. So have a quick check there. If there's anything that you need to have another look at, rewind the video and have another look at it, and have another go at some of those worked examples. See you again soon.